In this video, we're talking about visualizations of subtraction. So drawings, shapes, figures that will help us understand the concept of subtraction. So subtraction has three very important interpretations, and I want you to understand all three of these interpretations because they show up in different ways. And so sometimes one way makes more sense than another way. Sometimes one way is a little bit more straightforward or easier than another way. So I really want you to focus on the learning and understanding these three different ways to interpret subtraction. So the first way, subtraction is the difference between two numbers. So I have one number, I have a second number. How far apart are they? Second interpretation, a number taken away from another number. So I have a certain amount of money in my pocket, I buy something, I give that money away, right? I take that money away from my original pile. And number three, that any subtraction problem is actually an addition problem in disguise. So we know a lot about addition already, so it actually turns out that most subtraction problems can be flipped into an addition problem, and we can just use what we know about addition. As with visualizations of addition, you may love this slideshow and use all the ideas in it, or you may not, and you may only want to use some of the ideas in it or some of the models in it. The point is to find a way that you understand. Not just a model or a process that you can work through, but one that you really understand what's going on. So objects, this is the first model. We use this with addition too. In the most basic use, each model represents one, and this is a good model for subtraction as taking away. For example, 7 minus 2. So we start with 7 objects, so I have 7 circles. I'm going to take 2 of those objects away. Boom, boom. If I take 2 away, I'm left with 5 circles. So 7 minus 2 is 5. Objects is also a good model for subtraction as difference. So again, 7 minus 2, but now the question is, okay, here are 7 circles, and here are 2 circles. What's the difference? Well, the difference between the 7 circles and the 2 circles is 5 circles. So it takes 5 more circles or chips to make the 2 set of objects the same. So that tells me that 7 minus 2 is 5. Same ideas for objects hold with addition. You can use multiple objects. Maybe a circle is 100 and a square equals 1. Same idea. With decimals, with fractions, all the stuff we did with objects still holds with subtraction. The key is to designate the value of each object, just like with addition. Now a number line. This is another nice model for subtraction. So this can show subtraction as difference. So here I'm going to do 8 minus 3. So I have my number line already set up. And again, I'm going to represent my numbers with arrows, not dots. So this red arrow represents 8 because it has a length of 8. The purple arrow represents 3 because it has a length of 3. So if I want difference, I'm looking for what is the difference between the end of the purple arrow and the end of the red arrow. So if I fill that in with this green arrow, that's the difference between the short arrow and the long arrow. And the length of that green arrow is 5. If I go from the beginning of the arrow to the end of the arrow, I traveled a distance of 5. Here's 1, 2, 3, 4, 5. So I traveled a distance where that arrow has a length of 5. The number line is also good for subtraction as addition. So here's my 8 arrow and my 3 arrow again. And now my question is 3 plus what gives me 8? So notice, again, I'm just filling in that spot, the area that goes from the end of the purple to the end of the red, but I'm thinking about it a little bit differently. I'm saying, okay, 3 plus what gives me that red arrow on top? So again, I'm going to fill that spot in. I fill it in with a green arrow. It looks exactly like it did on the other page. The length of that arrow is 5. So this is telling me that 3 plus 5 equals 8, which means 8 minus 3 equals 5. Number line is also nice for subtraction as taking away. So I'm going to start with my 8 arrow again, and this time I'm going to take away 3. So I'm going to start at the end of my 8 arrow and sort of count backwards. So now I was all the way up here at 8, but I don't want to be there anymore. I want to take away 3. So I'm going to count back 3 places. And so where does that put me? Well, that puts me at the number 5. So again, I'm lining this up in such a way that the 2 tips or the 2 points of those arrows show up so that I'm going down the 8 arrow and then I'm sort of backing up that purple arrow. And so then what do I have left? Well, I landed at the 5. If I fill that in with an arrow, we say that the length of that arrow is 5. Or if you just want to say you ended at the 5, that works as well. So this shows me, again, that 8 minus 3 is 5. For number lines, same idea holds for multiple objects, decimals, fractions, just as they did with addition. So all of those things, the key here is to properly label your number line. So if you're working with fractions, make sure it's broken up nicely into fractions with denominators that you want. If you're working with decimals, make sure it's broken into tenths or hundredths or thousandths, whatever you need for that particular problem. Okay, bars, or a length model. So again, these are very, very common when learning fractions, and they're very useful for doing computation. So again, see the National Library for Virtual Manipulatives to actually play with a set of bars online, or to print out a set of bars that you can cut out and play with on your own. So let's do something like 5/6 minus 1/3. So here's my setup. So I have 5/6 stretching across the top, and then I have 1/3 underneath that, because I either need to think of this as taking away 1/3, or what do I need to add to 1/3 to get to 5/6? Whatever interpretation of subtraction that you're using, this is going to be the same general setup. So I have the 5/6 across the top, then the 1/3 across the bottom, and the answer is what fills in the difference between those two lengths. So to find those distance, we actually would play with our manipulatives. We would get out our toys and we would figure out what fits into that spot. What stretches from the end of my 1/3 all the way to the end of the 5/6. Now sometimes in your picture, like in this one, we can see what would fill that spot. But otherwise, using a bar or length model, we just play with those bars until we figure out what fits. Here we can see that that distance is 3/6. Because part of the top bar fits perfectly into that bottom part. Or if we played with our manipulatives, we might recognize or find out that a half fits there. Same idea for bars holds for decimals, whole numbers, fractions, everything same as it did with addition. The key is have actual bars, or if you're good, and you have some graph paper or a ruler or something, you can draw them to scale. But the key there is if you're going to hand draw this, you have to draw it to scale. Okay, area model, again, very helpful. I love to draw my fractions like this, so I'm going to show you a fraction example. It can also be used for decimals and whole numbers. Just be careful. Decimals, we tend to use 10 by 10 grids, so that only goes to hundredths, so careful if it goes past that. And then whole numbers tend to sometimes they get pretty large pretty quick, so be careful about that. But areas can be really nice for small number decimals that only go to hundredths, and excellent for fractions. So here we have 13/16 minus 7/16. So I'm going to draw those out. So notice I remembered this time to tell you how big the big rectangle was. So with any area model, it's very important to reference the size of those rectangles. And the easiest way to do that is to say what has an area of 1. So the shaded green is 13/16. So if you count up, I have 13 green boxes inside of my larger rectangle that has 16 parts. And then this purple color, there are 7 shaded, and again 16 parts. So I made the 2 holes the same size so it was easier to see. And now the question becomes, what's the difference between these two shaded areas? Or, what do I need to add to the purple area to make it exactly the same size as the green area? Well, it turns out I just need to fill in these boxes to make it look just like the green one. So that's what I did with the orange on the right. So what's the difference? The difference is just how many oranges. Well, that orange is 1, 2, 3, 4, 5, 6 pieces. And again, we still have 16 in the hole. So what did I add, or what is the difference? 6/16. Fractions get a little bit more difficult when we start with different denominators. So what about 2/3 minus 3/8? So I'll start with my drawings. Again, the large rectangle is 1. The two holes are the same size. So now I have, in the green, 3 equal parts, 2 of them shaded. With the blue, I have 8 equal parts with 3 of them shaded. It's very hard for me to compare these two areas as they are. And why is that? Hopefully you said something related to the fact that the pieces are different sizes. Getting a little bit repetitive here. This shows up a lot when we talk about fractions. When we're trying to add and subtract fractions, we need those pieces to be the same size so that we can visually see them. So let's make them the same size. You already know how to do this. So I made both rectangles split into thirds going in one direction and eighths going in the other direction. So that broke them into 24ths. So if I count these, I have 16 green rectangles, 24 in the hole. I have 9 blue rectangles, 24 in the hole. So now my 2/3 became 6/24 and my 3/8 became 9/24. So why 24ths? Because 3 and 8 both go into it. You want a number that is fairly easy to break the given pieces up into 24ths. Okay, so thirds, I just broke it up 8 the other way. Eighths, I broke it up thirds the other way. So why 3 and 8? Because those are the original denominators. Those are the original number of pieces in the whole. So again, I went 3s in one direction, 8s in the other direction. And that's going to work every time. It won't necessarily give you the smallest common denominator, but it gives you a common denominator. And that's fine. So now the question becomes, what's the difference? So for me, I wanted to rearrange those blue so that they looked more like the green, so I could figure out what was missing. So what I did is I took the 3 pieces that were sitting down here and I just moved them up here. Okay, so the blue still represents 9/24. I have 9 blue pieces that are shaded and I have 24 pieces in the hole. So now the question is, what do I need to add to the blue to make it look like the green? Or what's the difference in the area between those two shapes? Well, if I fill in where I put these purple blocks, then the area of the green rectangle, shaded rectangle, is equal to the area of the blue and purple shaded. So what did I add? I added this purple. If I want to count that up, I have 1, 2, 3, 4, 5, 6, 7 pieces that are purple, and I have 24 pieces in the whole. So 2/3 minus 3/8 is 7/24. All right, so what about decimals? So again, decimals are fine. We like 10 by 10 grids. We like them a lot. But 10 by 10 grids become problematic if we need more than 2 decimal places. But this one has hundredths and hundredths, so let's go with it. So first thing, we're going to draw them. So 43 hundredths and 27 hundredths. So in the purple, I drew 43 hundredths. In the orange, I did 27 hundredths. So then the question is, what's the difference between these two areas? Or what do I need to add to the orange to make it the same size as the purple? So what's the difference? To make the orange look like the purple, I needed to include these turquoise boxes. So now notice Over on the purple, I have 1, 2, 3, 4 entire columns and then 3 boxes. So making sure I had that over on the right, 1, 2, 3, 4 columns, and then 3 boxes in that last column. So what's the difference? What did I need to add? I needed to add those turquoise. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 turquoise. So that is 16 boxes, which is 16 hundredths. So I can rewrite that as 0.16. So in summary, drawings can help us understand what subtraction is and what it looks like. Drawings can be very helpful for finding the answer on some computations, but not all. And of course, for me, drawings are awesome for understanding and computing with fractions.